All right, hello everyone. In this video, we're going to be looking at the formal epsilon-delta argument that we presented in class. So let's get started. So in this question, we're asked to use the epsilon-delta definition of a limit to show that the limit as x approaches -2 of the function 2x plus 1 is equal to -3. So in these types of problems, there are two steps. In step 1, we're going to work backwards. We're going to work backwards from absolute value of f of x minus L is less than epsilon, and we want to do some algebra to work towards absolute value of x minus a is less than delta. Right? And what we're going to do first is identify the parts of the precise definition of a limit. So namely, we need to know our function f of x, our limit value L, and our value a. So first of all, a is the number that x is getting close to, so it's right here. So x is getting close to -2, so that's our value of a. So I'm going to put the value of a right there in the place of it. And I'm just going to observe, x minus -2 is the same as x plus 2. It's going to be a little bit easier for me to work with it if it's written as x plus 2, so I'm going to do that next. All right. Now I also know that f of x is my function. So there's my function 2x plus 1. So I've replaced f of x with the function 2x plus 1. And similarly, L is what the limit is equal to, -3. So I'm going to replace L with -3 right here. Right? So my goal in step 1 is to work backwards from this expression to this expression. And the goal here is really to figure out what delta should be. And we'll see what that looks like next. So the first thing I'm going to do is I've got a minus a -3, so that's easy enough to recognize as plus 3, right? A minus a negative makes it a plus. And I'm going to combine the plus 1 and the plus 3 to make 2x plus 4, right? Now, again, I'm trying to make this look like something like this. So the coefficient down here that I'm working towards is 1, right? The coefficient of x is 1 here. Here the coefficient of x is 2, so I want to factor out that 2. Here's what it looks like when I factor out that 2. If I factor out 2, I get left over x plus 2 after I've factored it out. And this is very, very good because this x plus 2 looks a lot more like this x plus 2. Right? In these types of problems, after I factor out whatever the coefficient is, the stuff left over had better look exactly like the stuff below. If it doesn't look exactly like the stuff below, then chances are I've made some sort of mistake. All right, so I factored out the 2. I can use a law of absolute values to separate it this way, right? If I've got two things multiplied, I could take the inside an absolute value. I could take the absolute value of each of those things separately. So I'm going to take the absolute value of 2 and the absolute value of x plus 2, like so. And again, we're getting very close to the thing that I want it to be, right? Which is absolute value of x plus 2 is less than delta. So the only other thing that I really need to do is to take this 2 and put it on the other side. So there I've done that. So I've divided by 2. So I'm left with absolute value of x plus 2 is less than epsilon over 2. And now these two look exactly alike as long as I let delta be equal to epsilon over 2. And remember, the whole point of step 1 is to find a relationship between delta and epsilon. And now that I see these two expressions, I see what delta needs to be in order to make this argument look right. So we should choose delta equal to epsilon over 2. Right? That delta should be equal to epsilon over 2. Right? And we'll just keep that in our brain, and we'll use that when we do step 2. All right? So that's the conclusion of step 2. So let's go to that's the conclusion of step 1. Let's go to step 2. In step 2, we want to present our formal argument. So we're going to go through step by step what the statements in that formal argument are going to look like. So first, we'll let epsilon be a positive number. Next, we'll choose delta equal to epsilon over 2. It's exactly the delta that we found at the conclusion of step 1. We will assume that x is not equal to -2, so x is not equal to the a value that we started with. And we'll also assume that the absolute value of x minus a is less than delta. Right? That is, the absolute value of x minus -2 is less than delta. Then Now I'm going to take this is the same thing as f of x minus L, and I'm going to manipulate this expression to make sure that this expression is less than epsilon. So in step 2, I'm presenting a formal argument to show that this choice of delta works for the definition of a limit. I'm making sure that when x is in the orange vertical region, I want to make sure that f of x, or the y value, is in the blue horizontal region. Right? That's what I'm doing. So I'm presenting a formal argument that shows that that's true. Right? So a lot of this slide will look a lot like what we did previously. The work will look the same sorts of calculations that we did on the last slide. We're going to do here. So the first thing I'll do is I'll start with my f of x minus L, and I'll replace that minus 3 with plus 3. Right? So sorry, minus a negative 3 with plus 3. Right? I'm going to combine my constant terms, the 1 and the 3, add together to make 4. I'm going to factor out a 2. I'm going to separate it using the absolute value rules. Right? And now I'm going to replace this. I'm going to rewrite x plus 2 as x minus negative 2. The reason I want to rewrite this as x minus negative 2 is that way it looks more like my original assumption. Right? It really needs to look like x minus a. So I'm going to rewrite x plus 2 to make it look like x minus something. In this case, it's x minus negative 2. And now that I have 2 times x minus negative 2, I'm going to use this original assumption that we had up here. Right? We know that x minus negative 2 is less than delta. So this would tell us that 2 times that x minus negative 2 must be less than 2 delta. One way to think about this is if I take my original inequality here and multiply the left-hand side and the right-hand side by 2, I get 2 times this x stuff is less than 2 delta. And that's what I've written here. 2 times that x stuff is less than 2 delta. Right? Okay, now the rest of the argument is very straightforward. I'm going to replace delta with what it's equal to. Right? We chose delta is equal to epsilon over 2, so I'm going to replace delta with epsilon over 2. I'm going to cancel out my 2's, and I'm going to be left with epsilon. And this is good. This is exactly where I want to be. So I'm going to say we win. Right? We have shown that the absolute value of f of x minus L is less than epsilon. And a word also about this notation. So this notation can be very confusing. All of this chain of equalities and inequalities here, what this means is that this expression is equal to this expression, and this expression is equal to this expression, and this expression is equal to this expression, and so on. So what it's saying is that all of these things that are written here are equal to one another. They're all the same number. They're different ways of writing the exact same number. Whatever number that is, it is less than 2 delta. And 2 delta and 2 epsilon over 2 and epsilon, those are all also different ways of writing the same number. So all of this is one number written in different ways, is less than this one number written in different ways. So in effect, we have shown that this number, the absolute value of 2x plus 1 minus negative 3, same thing as absolute value of f of x minus L, is less than epsilon. And that's what we have to show in this step 2. Okay, so again, I just wanted to talk through a little bit what that notation means. Now the other thing that I want to do is I want to connect this argument with the formal definition of a limit. Okay, so I'm going to get rid of some of this middle work here. Right? I got rid of all that algebra there. It still should be there, but I need some space to write the next part. So again, just keep in mind I've taken away all my algebra, but I've still sort of got that final statement here. Okay? Here's what the epsilon-delta definition says. For every positive number epsilon, there is a positive number delta such that for x not equal to a, when the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So when we're showing that a limit exists, we have to verify this epsilon-delta definition. This definition gives us a template by which we will present our argument. So every part of this epsilon-delta definition needs to be in step 2. So this explains exactly why the words were chosen and why the order was chosen here in step 2. So let's go through that bit by bit. Right? The epsilon delta definition starts out for every positive number epsilon. The first step of our formal argument is let epsilon be a positive number, so they match up. Right? The next part of the epsilon delta definition is there is a positive number delta. Notice that the next part of our formal argument is choose delta equal to epsilon over 2. I'm saying what delta exists, right, in the formal argument. Next, it says for x not equal to a, so we'll assume that x is not equal to negative 2. A in this case is negative 2. So again, there's a matchup between the epsilon delta definition and the steps of the formal argument. When x minus a is less than delta, right, we're assuming that x minus a is less than delta. And the last step is, then we have to show that f of x minus L is less than epsilon. That's exactly what I'm doing here, right? This part corresponds to this part here. I should have put this in blue as well. Sorry about that. So this just shows that every part of the epsilon delta definition occurs as a part of the formal argument, and it occurs in the same order. The wording is a little bit differently because I'm presenting that argument instead of stating the definition, but understanding or memorizing this definition will help us understand the steps for the formal argument. All of these are very, very similar. This process works for linear limits, limits of linear functions like ax plus b. And if you have questions, please let me know. All right. Thanks very much.